Okay, again, welcome everyone to today's session of Shadow the Scientist. And we do have two of our scientists, astronomers, who will be shadowing today as they use the Keck Observatory. They did already introduce themselves off camera, but as we've just started our recording, I'd appreciate it if you would both reintroduce yourself and then give us a bit of background on the instrument you'll be using today and your research goals.
Okay, so hi everyone. My name is Joel Roediger. I am an astronomer working for the National Research Council Canada, and I'm located in Victoria, British Columbia, Canada. And as I said, very fortunate to be using Keck and the ESI instrument tonight to observe some galaxies in the relatively nearby universe. And Eric, I'll let
you up, and when the exposure's done, I'll start our slowly back to the loud.
Okay. So are we on the last exposure of this right now, Joel? Sorry, we have to actually do something right now.
So we are on our second exposure, less than 3 minutes or 5 minutes to go.
We have 5 minutes to go. So it sounds like Tony says we're going to hit the elevation limit just as this exposure finishes. So maybe we want to queue up the next the target, which I guess will be the one that we had some trouble with on the star list. Is that right?
No, it's not actually. It sounds like the star, the RR Lyrae star, wasn't actually a problem. It was a different one. So I will highlight the next target. So if you want to communicate that to Tony, and yeah, we can stop after the second exposure.
Okay. We're going to queue up the next target in the star list, and
so everyone's getting treated to seeing things happening in real time.
I guess we got about 3 minutes.
Yes, that's what I love
That's
about
good.
these sessions. These are live, real-time experiences with you all as you are getting data. So we will quietly listen and let us know when we can re-engage with you.
All right. I think so we're gonna slew to the next target in about 3 minutes is what we're doing. And I have to disappear for a couple minutes, but I know, Joel, you can tell everyone what's going on.
Okay, but if Tony needs to talk to me,
I'll be okay. It looks like we're okay for the next target. I just need to duck out for a sec here.
Okay. Yeah, so very quickly I can tell everyone sort of why things are happening this way right now is that so Keck has 2 telescopes, and the telescope that we are using tonight, when it's pointing towards the western half of the sky, it can only go down to a certain elevation before it runs into something called the Naismith platform. The Naismith platform is where the instruments sit around the telescope. And so this Naismith platform imposes a constraint on how far we can point downwards towards the horizon. So we're approaching that limit as we're tracking the object that we are exposing our instrument on right now. So in just about 1 minute, we'll be finishing our second of 3 exposures that we had planned on this galaxy. And then we are going to stop what we're doing. We're not going to take that third exposure because of this elevation constraint. And instead, we're going to transition to a different part of our science plan for the evening. So we started observing with the telescope about 4 hours ago, almost 4 hours ago. And so we've been observing galaxies, as I said, from the nearby universe for the past 4 hours. And with the time remaining that we have in the night, we're going to look at something completely different, which is a star that is in the very outer reaches of our own galaxy, the Milky Way. It's a star known as what we call a RR Lyrae. So that's a type of variable star. Okay, so now I need to stop our exposure. And that will, and then there's someone at the telescope on the summit of Maunakea that is going to actually move the telescope to a new target. I may actually in a second be able to share my screen with you so you can kind of see what's going on. Jimmy, is that common? Do people show the display of the instrument controls?
Absolutely. You can totally share what you'd like. Let me make you both co-hosts. Thank you. Mm-hmm.
All right. Okay, so we stopped and now we are. Oops.
All right. Yeah, that's right. We'll want parallactic angle.
Okay.
So we're slewing to the target now.
Okay, so this is now I'm sharing with you one of my 4 screens that we use to I guess control the instruments that we're using, to get a picture of where the telescope is pointing at on the sky so that we can see the target that we're looking at. Okay, so sorry, 1 second. I realize. Oh, are we exposing?
We are.
Yeah.
Why are we exposing?
I do not know, but I think I should stop it.
Wait a minute. Is this the second? Did we only finish 2 exposures?
We did, yeah. So
so we had set up 3, right? But we have to yeah, I think you just want to, well, just stop and read out maybe.
Sure.
It's a little bit safer.
Complete.
Okay. And I'm going to adjust. So what you can see right now in this
ACS sensors are saturated. ACS sensor range is not normal.
What you see in this right-hand panel here is a view of what's called the guider camera. So this is looking at the focal plane of the telescope. And so it allows us, what we use it for is to help with finding the target that we're looking to observe, and centering our instrument on that target. So, it's not as easy as just saying, okay, I want to go to these coordinates, and at those coordinates that I point the telescope at, I will be looking right at the targets. Sometimes you have to do a little bit of fine tuning of the telescope pointing. So that's what you see, all this motion happening right now is just things are whipping by as the telescope is moving or slewing to the new target. Eric, could you please ask Tony to align the slit with parallactic angle for a 15-minute, or actually we're going to be exposing for 45 minutes.
Okay.
Okay, so right now I'm just updating the exposure time for the instrument.
Yeah, so I guess we're gonna be on this for about 45 minutes, I think.
So I'm setting the exposure time to 15 minutes, and that we will do 3 exposures of our target at 15 minutes each. So we'll get a total of 45 minutes worth of exposure time.
And you can see this
There is one extra line.
star.
Yeah,
Yeah,
it's a little bit I mean, I
disappearing.
apologize.
Yeah.
Yeah, it's so if you look at the bottom of the screen here, what you could see are these slits.
Okay, I've got your target in the slit. You can't see it, but it's in there. And,
Yep, we saw it go in.
got a
Mhm.
yep, I've got a guide star here, so looks good.
Okay.
Okay.
I think
All
we're
right, so
ready to go.
Yeah, we're ready to go. And actually, should we get a seeing measurement first? Get a focus measurement, just because I know Raja wanted to change the slit depending on the seeing.
Well, we've moved quite a bit. I don't know if
So we're at air mass 1.1 or 1.2.
I don't know. It's been well,
There is one.
but you were saying we should do a focus, or what we're
Yeah, I think it would be worthwhile to do that, just so that we know if we need to because I over the course of the previous observations, we were seeing the guider seeing getting worse steadily. That could just
Oh.
be, that we were going to lower air mass or higher air
I
mass.
think it probably was, but I don't know, Tony,
But,
do you think that
I think it'd be nice to
the image quality is degraded much, or I mean, would it be worth?
Really, no, I mean, conditions have been pretty stable in the second half of the night. I don't really know if it's worthwhile to do that. Do you have any better seeing measurements? Tower seeing's not
My instinct is just to go, because I think we're back up to a higher elevation, and it would probably be okay.
Yeah, I mean, I really think it's pretty good here. I don't think we're gonna get much of any improvement with the focus.
All right.
Personally.
Okay. All right. I've started the exposure.
Okay, well, so we've just started the exposure then. Yeah.
Okay.
All right.
Okay.
Thanks.
So just so people understand, so with this guider view, when we are pointing in the direction to where our target is located on the sky according to its coordinates, then we need to align that target onto one of these dark rectangles down here. These represent what are called slits for the instrument. So the slit is basically like an entrance aperture. So that's the light from the object will pass freely through that slit. The light from everywhere else on the focal plane doesn't pass through. So the slit that we're using right now, I don't know if you can see my cursor, is the one that I'm tracing out here. And so the object that we're looking at, which is a star, is located is centered on that slit there. So that's why you don't actually see it. But we are confident that we've acquired this target well, and that our slit is centered on the target, and now we are exposing the instrument, the CCD of the instrument, and collecting photons from the star. So it might be a good point to sort of give people an idea of what this instrument actually is. So ESI, it stands for, Eric, maybe you can help me with this. It's, I think the first word would be Echelle.
Spectrographic spectrograph and imager. I think that's right.
Yeah. So, so at the most sort of basic level or basic distinction of what this instrument is and what it does, is it is a spectrograph, which means that it takes in light from astronomical targets or objects, and it'll pass that light. You can think of through a prism, which spreads out the light. But in our case, it would be using something different, not actually a prism, a grating, and that disperses the light into its individual wavelengths. So whenever we see light, say with our eyes from an object, we see a lot, or we receive photons of many different wavelengths, all from the same point. What a spectrograph does is it then actually breaks that all that light up according to the wavelength, and then spreads that light out onto a detector. And that allows us to see how the light, how the amount of light that we're receiving changes as a function of that wavelength. And so that is really powerful. It's a powerful method in our toolkit for understanding the nature of astronomical objects. So currently we are observing a star, as I mentioned before. It's in the very outer regions of our galaxy, in a place that we call the halo of the Milky Way. And with these data, we will be, I believe the goal, it's not, I'm observing this as a courtesy to our collaborators on this program, but I believe the goal of this observation will be to determine the distance to this star in our galaxy.
So maybe I could say something about that, since I'm a part of that program.
Excellent.
These stars, these RLR stars, are these pulsating stars where we can, just from the brightnesses, we can measure the distance to them. But what we're trying to do with the spectrum is get a velocity for the star by measuring the Doppler shift. And the idea being that we want to measure the velocities of stars in the very, very outer halo for a number of reasons. One is to that their orbits, the velocity of their orbits correlates with, it depends on the mass of the Milky Way. So it helps us measure the total mass of our own galaxy. And the other is that there are some, so galaxies don't just live in isolation, they also assemble by absorbing other galaxies that merge with them. And it's increasingly being understood that the Milky Way is merging with some smaller galaxies, some satellite galaxies, and there's one galaxy, the Large Magellanic Cloud, which is the largest of the satellites around the Milky Way. It's some theories and some simulations have shown that it's possible that we're in the stages of interacting with it, where the Milky Way is actually kind of in a reflex motion in orbit or with that smaller galaxy. And that would be seen by seeing an offset in the velocities of these very distant stars. So we're also looking for that, the sort of reflex motion of the Milky Way kind of being jerked around gravitationally by one of its smaller satellites. And so we have to observe not just one star, but many stars, tens to 100 stars, to try to get a mean velocity for these distant stars. So that's the goal of this program. And these stars are spread out all over the sky. So when we, just as you were joining, we were having this issue of we had to finish one of our exposures because the telescope was pointed too low, because we were chasing our targets, galaxies down into the west. And then we are now switching to these targets, which we have lots of that are all over the sky. So that's a bit of why we're doing this. And we're going to be observing, I guess, Joel, do we have one or two of these stars? I don't know how many we're planning to.
Just one.
Just one. Okay. And then after that, are we going to do template stars?
Yeah.
Do we have time for that?
We will. I need to check our where we are versus twilight, because I do want to observe a flux standard, or we call it a night. So let's see, we're halfway through the first exposure, so 7.5 minutes. So then we have another like 30 half hour, 35 minutes. So it'll be, yeah, we're gonna be right up against twilight, I think, once this is done.
Oh, okay, already. Yeah,
So
because
I think we will
twilight
be moving
is
to our flux standard after this.
let's see.
But I I want to thank you, Eric, for correcting me on the record of what this.
Oh no, I mean I'm actually part of.
I absolutely should have known better. But as soon as you said it, I was like, no, we're actually doing a velocity. I was like, oh yeah. I do know enough about this program that I should have. I think it's the end of night, and I hit a mental there.
No, it's all right.
There is.
I should know this since I'm part of the program here. So,
Yeah,
but
no, I'm glad you jumped in.
yeah, I guess it looks like so twilight was at 12 degree or 18 degree. Raja said that 18 degree twilight. Well, I have here that twilight begins at 8:30 Pacific time. 8:33, 5:33 Hawaii. But I can't remember if that's 18 degree or 12 degree.
Yeah, I'm just looking at my elevation chart here. So I have twilight at local time in Hawaii at 5:07 a.m.
5:07. Okay, so that must be 18 degree then.
Let me check here or something.
And what we're referring to is that
12 degree twilight is 5:30.
Okay, so that's just 12 degree twilight is when the sun is 12 degrees below the horizon, and 18 degrees is when it's 18 degrees below the horizon. And typically the start of what we call astronomical twilight is 18 degree twilight. So when the sun is 18 degrees below the horizon, you start seeing a bit of a glow in the sky, and the sky starts to brighten a bit. But you can still observe at 18 degree twilight, especially if you're observing brighter targets. 12 degree twilight, I think it's usually called nautical twilight. I don't, without being a sea person, I don't know why, but and then 6 degree twilight is often called civil twilight, which is when basically when street lights come on, when your car lights have to come on. So, but we will, I think usually we observe from 18 to 12. If we do some brighter objects, then after 12 degrees, it gets pretty bright, pretty fast, especially with such a huge telescope as Keck is. You gather a lot of light. So you said that that's at 5:07 or something like that, Joel?
Yeah. So yeah, I think 18 degree will be 5:07 and 12 degree will be 5:30.
Okay. Well, so this session will end before all that happens, but twilight tends to be a little bit frantic because you don't have that much time. The sky's getting bright and you're trying to hit some bright targets, a few of them one after the other. Okay, so we have a question in the chat. It looks like, why is the aperture a slit and not a round hole? That's a really good question. If you were only interested in the star itself or the object you're observing, you could have a round hole, and then you would get just the light of that star through the hole, and then you would disperse that. But with the star that you're observing, you are also observing what we call the sky. The sky itself is not perfectly dark. The parts of this image that you see here that are not filled with stars actually have emission as well. The sky itself glows. There's background light in space. There's the atmosphere that glows. It gets heated in the daytime, and then the molecules emit light in the nighttime. And so when you get a spectrum, you're seeing not just the star of interest, but also, or galaxy of interest, but also all the light that's emitted by the sky. And so you want to be able to separate that. So we have this slit so that on either side of the target, you get a spectrum that is that is sky. And I don't know, Joel, if you want to share the readouts window so that we can see what a spectrum looks like.
Sure.
And then, so what you can do then is you can take the spectrum on either side and use that as sky and subtract that off from the spectrum that contains the object. And so,
fortunately, this display is not so great because this was the exposure that was started while we were slewing. You can
right.
kind of it's I can try and kind of train. We'll get a better one in a second. That'll it's actually we have less than a minute on this current exposure.
Okay, yeah.
This will all be lit up or illuminated a lot more clearly. You'll be able to see what Eric is talking about. He'll be able to point out, okay, what is the object on this image? What are the sky emission lines? The air glow and all that. So
there's another question here saying, what is the magnitude of the RLR star? 45 minutes on a 10-meter telescope. Sounds like it must be awfully faint. Yes, well, 10-meter telescopes we need them to observe these the faintest things. I don't know about this specific one, but this sample, I mean, these objects are probably in the G band, I'm guessing around 21 or maybe 22nd magnitude. And if that means anything.
So now you're going to start seeing the
here we go.
As the window's changing, you see this line. This is this line moving down, and the display is changing in the top half. So this is just showing that we're reading out the detector on the instrument, and we're populating this display with new data. So now you can see. So you can go ahead, Eric. And
no, it's okay. I was wondering if you can change the the stretch or something here.
DCD readout complete.
How's that?
It's a bit better, yeah. Well, I don't know why it's so. Can you tinker with the? I guess it is already at histogram equalization.
Yeah, it's very sensitive. So I'm controlling this, these displays remotely from my office in Victoria, BC, to issuing commands to computers in Hawaii. So I think that might be the best I can do without.
Yeah.
Changing,
I see if
you have the VNC working?
Sorry, yeah, I have the VNC working.
Okay,
so
okay, yeah.
Play
All right,
with it
take control, please.
Let's see, auto display.
That's not bad.
This is not bad, right?
You definitely tell it's a faint target.
Oh, okay. Now let's see what happens if you. Did I overdo it here? Oops, that was a
Yeah, having the same issue as me with the mouse.
Yeah, the mouse, yeah. So oh, how did you do the stretch thing? Was it
right click, just
click.
Well, for the way I have set it up is right click.
Okay. Yeah. I don't know if it's any better, to be honest. Actually, it's worse. So No, my option key, my command key doesn't work here. Well, I'm gonna. So maybe I'll let you re-stretch it because I'm not having a lot here.
Okay.
It was better for a sec, and then I hit.
Are you doing that by a mouse pad?
Yeah, a mouse pad. I'm using a mouse pad,
Okay.
which is
Yeah,
harder.
I have
Okay, there you go. So so what you're seeing here are these sort of vertical bands, each of which is a part of the spectrum. The light goes from bluest on the left side. Blue is top left, and then it goes redder, and then it goes over the next one, gets redder, and then all the way here on the right, we're nearly in the infrared. This central line here is the actual star spectrum, and you can see it's nice and narrow. It's really sharp. So it looks like we didn't really need to focus, which is good. And then, so the star is only the size of a small dot, right? That's why it has this narrow, when you disperse it, it has this very narrow line. But then the slit, the full width of the slit is the length of this kind of a line. And so can you see it if I move the cursor? Am I moving the cursor and you?
Yes.
Yeah, okay. So then this line is a skyline, is an emission line from the sky itself, and that's why it fills the full slit. And you can see all these other lines here. These are all mostly, I guess, OH lines, so hydroxyl lines in the atmosphere. And they get space as you get closer to the infrared, there are more and more of them. And so if you want the spectrum of the star, for instance, at this location, you want to know how bright the star is, you have to take the flux of the line on each side, sort of interpolate over here and subtract that from the value in the middle. And so that's the tail end of the question, like why we have a slit as opposed to a small circle. So I'm going to go back to view only, so I'm not screwing up the mouse for you and the VNC.
So let me I can try and so that is a view of the spectrum, the data on the detector itself. Of course, then a lot of there's other work that needs to be done to actually get a spectrum extracted from an image, and we colloquially refer to this as reducing a spectrum or reducing data. So I want to show you, if I can. Here we go. Okay, so I'm going to start a new share. Okay, so one of our colleagues who was on the call with us, he's located in Hawaii, works for Keck, so he was our support astronomer for tonight. He helped us out getting a tool on the computers in Hawaii to actually work on doing this so-called data reduction for us, so that we could have a look in real time at the quality of the data that we're getting. So this here is a display of one of the end products of these exposures that we've been obtaining tonight. So this is actually for one of the things that we were observing earlier in the night. So this is showing you the spectrum of a galaxy, and this spectrum is broken up into chunks And we're showing it in 12 or 10 chunks in total. And that just has to do with the way the Echelle spreads out the light on the detector itself. So Eric showed you that image that we got from our star, and there was basically these 10 different orders, as we call them, of the spectrum. And on each order, you get a different range of wavelengths. And so that is what you can see here is that each of these panels in this graphic show you the spectrum at different wavelengths, going from the very blue edge of the optical window out to the red end, getting towards the infrared. And so with these data reduction tools, we can go into the images themselves. We can identify where the object, where it lies on the detector in all of these different orders. We can then sum up the light from the object. And as a function of its wavelength, as a function of the wavelength of light, we can also subtract off all of those sky emission lines, so that we can basically just see our object itself. And so this is what we get out in the end. This is the spectrum that we're hoping to measure for all of our targets that we've looked at tonight. And so what is the thing that we're ultimately going after within these spectra are these dips you see here that I'm circling with my cursor. So a dip in the spectrum like this, these are created by either individual atoms or molecules in the atmospheres of stars in the galaxies that we're looking at. And we can use those dips, or what we call absorption features, absorption lines or absorption bands, to actually diagnose the physics of these stars in these external galaxies. And by knowing some of the physics of these stars, that gives us a window into what has happened throughout the lifetimes of these galaxies. So one of the things that we're ultimately trying to get out from these data is an idea of when did these galaxies form their stars, and how quickly did they form their stars. This observing program that we're conducting, we've been running it for a few years now, collecting data both from the Keck telescope and from the Gemini observatory. And we've been able to uncover some interesting patterns in the properties of stars that, and the properties of galaxies that live in the densest environments in the universe. So in sort of one sentence, what we're finding is that the galaxies that are in the very centers of galaxy clusters, they seem to have formed their stars a very long time ago into the past, and they formed their stars quite rapidly. And so with this program that we're currently running here at Keck, we want to try and measure these properties for more galaxies and build up a statistical sample of objects that we can then take these measurements from real galaxies and confront those measurements against theoretical models of how galaxies form, and how the formation of a galaxy and its evolution depends on where it is formed. You know, if it's formed in a dense environment versus you know, an environment that is more rural in the universe. Okay, So now I need to check and we'll see where we're at. Okay, so we're still exposing, doing our second exposure on our RR Lyrae star in the Milky Way. Coming up on 3 minutes remaining on that exposure.
So this is the second of 3, right?
Yes.
Okay.
Could either of you give us a brief explanation on the name of our Lyrae stars?
Well, it must be because the original star studied was in the constellation Lyra. I don't know why RR. I've always wondered that actually, because usually the stars are, named alpha, beta, gamma, etc., based on their brightness. And but the RR designation, it must be quite old. I mean, you see references to RR Lyrae stars from like over a century ago.
Oh, wow. So these stars were discovered, this type of star was discovered a long time ago then.
Yeah, fairly early. Yeah. I mean, in I think probably telescopically, but still, I think it goes back, because I know that one of the papers we cite in this paper we're working on is from over 100 years ago. So I think I'm guessing that it has for some reason, the original star that was discovered to be variable was designated RR for some reason. And often is the case, like, there's a variable star class called Cepheids, and that's from a star in the Cepheus constellation. And that is found to be variable. It's like the prototype of it. But I've never actually, it'd be fun to observe RR Lyra itself. Probably not with Keck though. It'd probably be too bright.
Yes, that would be the star that started them all.
Yeah, that's right. But typically they're kind of so they're a variable star of a specific kind, in that they are helium burning. And so most stars you find are burning, like the sun, are fusing hydrogen into helium in their cores. But then, and that powers a star for 90% of its lifetime. But after it runs out of hydrogen in its core, then you have this helium core, which starts collapsing and gets hotter, and the outer layers of the star then become a red giant. But then once the helium core gets dense enough and hot enough, it will start fusing from helium into carbon and nitrogen and oxygen, and making those elements in the core. And when that happens, the star sort of shrinks a bit again. And then some helium burning stars end up in this state of variability, sort of a metastable state, where it goes from a smaller state, and then it pulsates, it becomes larger, but then it kind of collapses again, and then it does this. And the variability is on anywhere between a 6 and 24-hour time scale. So the pulsation is actually quite expected, and you can predict that from physics. But what's going on inside the star is it is fusing helium into these other elements. And so what you hear there is the exposure finishing. But yeah, so this star that we're observing is currently got an envelope of hydrogen, but in the core, it's fusing helium into carbon, nitrogen, and oxygen. And then eventually it will, I think, and these are low mass stars that don't have very many heavy elements. So they will eventually turn into white dwarfs. The carbon, nitrogen, oxygen core will not be able to continue to fuse, to get hot enough or dense enough to fuse into heavier elements, and so you end up shedding the atmosphere of the star, and then you're left with the core, which would be a white dwarf.
Okay. And so thank you, Eric. And so since this star is fusing helium into heavier elements, I would assume it's no longer on the main sequence.
That's right. It's on the what's called the horizontal branch in the Hertzsprung-Russell diagram, which shows the evolution of stars. But yeah, so it's in that kind of 10% of the lifetime of a star where it's not burning hydrogen. Thank you Daniel for putting this in the chat. I was thinking that Wikipedia must have an answer to this question. And that, yeah, and I was wondering if RR was just because they had run out of letters. Yeah, so there you go. It's sort of probably not that bright a star, actually. I mean, it's not naked eye, at least. Yes, it looks like, I'm looking it up now. Oh, it's a roughly 7th to 8th magnitude, depending on what stage of the variability it's in, which is is fainter than what you can see with your eye. So its variability would not have been discovered before telescopes, as opposed to other variable stars, which have been, which were noticed by ancient astronomers. Okay, so there's another question here. The light from the star correlates only to that center line intersecting each horizontal band in the first spectrum display. That is correct. The central line is the light from the star we are interested in. All those other bands, horizontal bands, are emission lines from the sky. Actually, if we weren't pointing at anything, if we were just pointing at blank sky, we would still see all those horizontal lines, but we wouldn't see that central line down the middle. And so the spectrum that Joel showed, which was the reduced spectrum, those that was the flux of that central line as a function of position in sort of vertical position on that image. But it had the sky already subtracted, so that's why you don't see big spikes every time you have a horizontal line there, because that way you get a better view, a quick view of the spectrum.
I would like to know how, so you mentioned data reduction. How long after you get the data, let's say just the data from the 3 exposures that you're doing of this particular star, how long would it take to actually get usable data from what you are receiving now?
So this is my first time using this instrument. So I don't have previous experience with data reduction for it. But what I can say is that in using the computers at Keck to produce this quick look data reduction that I showed you before, this was done via a pipeline, which is just basically you stack a whole bunch of recipes together, conventional recipes with sort of default settings. So it's not really like something that you necessarily use for doing science. It's just have a quick look at the data. But I would say that ran in a matter of minutes. Was my impression. So there's other kind of preparations that also need to be made, like whenever you're reducing data, you have to use what's called calibration data. So calibration data will track things like there's with any kind of CCD detector, there's usually what's known as a DC offset. So there's you don't start counting electrons on the detector from 0. There's usually a sort of finite floor that's you know, the detector pixels of the detector are populated with, and but that floor is not perfectly set across all the pixels, so you kind of need to know, okay, like, oh, this pixel has a little bit, you know, starts out with a few more electrons than this other one, that sort of thing. So there's all these kinds of you know, say either imperfections in the detector, or say the illumination of the instrument is uneven. That all of this needs to be tracked in order to actually do a proper data reduction. So it can be longer than that. So we had the benefit that our support astronomer had made available some of these calibration files that we needed. So that allowed us to just basically run this pipeline tool, and it produced this quick look spectrum for our targets within a matter of minutes. So it can be as short as that, but usually it takes longer, especially when you're doing science quality reductions.
Oh, yeah, that totally makes sense, Joel. Thank you for that, for those insights. And I think we have our last question. We're at the top of the hour from Joseph. Are there major differences in early morning versus late night astronomy?
Yeah, how awake you are. Well, I guess it's early morning is late night, in the sense that even though I think most of us are probably somewhere where the sun has risen already, in Hawaii it has not yet. And so but yeah, this program we've only been on since for the second half. So we started at roughly 12:30 a.m. Hawaii time. And so sometimes nights get divided into different halves for different groups. So it can be a little bit rough sometimes to be, but when the weather's good, you never complain.
So I could add to that is that, you know, why we were scheduled to use the second half of the night is because for whenever you are you know, observing with the telescope, you always have a certain set of conditions that you want to be observing in, depending on how bright your target is. You know, what is your tolerance for things like, you know, a certain amount of cloud cover, that sort of thing. So in our case, when we proposed to use Keck, we had determined that we need to be observing our targets when the moon is not up in the sky, because the moon adds to the overall kind of background illumination, or the overall brightness of the sky. And you know, when you're observing at bluer optical wavelengths, that can degrade the overall quality of the data if you have the moon there. So in our case, we got scheduled for the second half of the night because the moon had just set before we got on the telescope. So conditions can change throughout a night, sort of thing, and that can determine, you know, who gets access to the telescope, depending on what they need to do their science.
Great. Thank you so much, everyone, for joining us today in the chat. Thank you for everyone's questions and comments, and I got some direct messages too. Thank you so much for those. And we really, really would like to give a huge mahalo nui loa to Eric and Joel. Thank you so much for allowing us to shadow you as you use the Keck telescope on the summit of Maunakea. We hope you have a good rest of your observing session. And to everyone who is joining us, have a wonderful Monday. Aloha.
Thanks, Jamika. Thanks for coming, everyone.
Yeah, thanks, Jamika.
My pleasure.